So hello everyone, this is Ghulam Husain and I am pursuing my MSc Physics from IIT Patna, and today I'll give a brief introduction and lecture upon Kepler's law. So starting and learning about the Kepler's law, first we should know what is who was the Kepler. So Kepler was a German mathematician and astronomer. He was the scientist in 17th century before Newton, and he has delivered three main law, and he was famous for these law which were the best. He was best known for the discovery of the three laws of planetary motion. Okay, so before Newton he gave three laws, and today's day, like in 21st century, these three laws are still very accurate, and nobody has found that of course there will be changes, but he was very correct about it. So we shall start about this. So moving towards the first law of planetary motion, which is law of orbit. What it says, all planets move in an elliptical orbit with the sun at one of its focus. Okay, so considering the rotation of planet in our universe, in our solar system, we should know what our planets are moving, how they are revolving, how they are evolving. Like, so they are not at all moving in a circular orbit. Like we think like Earth is moving around the sun in a circular orbit. Like in our childhood we seems to think like this, but it is not possible. It is not happening. He said that like it is the Earth is rotating in an elliptical orbit around sun, and one of its focus has the sun. So this is our sun, okay, which is present at one of the focus, and the Earth is revolving around this path, this green path, which is an elliptical path. So there is a term and very important physical quantity, eccentricity, which tells about how circular or how your motion is. So in this motion, your eccentricity is zero, in between 0 and 1. Okay, for circular motion you have eccentricity somewhere around e is equals to 0, but for this kind of motion, like elliptical motion, our eccentricity is 1, and eccentricity is, of course, as I told you, it is tells you about like how circular, how elliptical, how parabolic your motion is. So moving forward, there are some physical quantities and parameters through which we measure our system. Okay, so this blue line you see this here is a semi major axis, and half part of it is a semi major axis, other half part is semi minor axis, which is this. So this is semi minor axis, which is a complete minor axis. This is a major axis. So this by this cross we locate our planet in somewhere around in an orbit. Okay, moving forward, we know that Kepler has given the second law, which is law of areas. Okay, so what is law of areas? A line joining any planet to the sun sweeps equal area in equal time. And in other words, we can also tell that aerial velocity of a planet is constant. So basically, what is aerial velocity, or what is like what Kepler trying to say? So by this concept, you'll know like how our even weathers and these things are changes. Like in summer, where is our Earth is, okay, and also you can estimate most oftenly many things with that. Okay, so how here is a very small and brief derivation for this. Okay, so moving for that, like how aerial velocity is constant. So area, if you consider this is a radius, you can say it as radius, and you can consider this a small angle theta element. So this sector, okay, you can say this is r del theta. By this you can say that area is 1 by 2 r square into del theta. This r square theta is this r into r theta, r del theta. Okay, this was r square del theta. Another one of the very easy approach to find out the area per radian is area per radian, like theta will be, what is the area of a circle? Considering an ideal example with a circle, area will be a pi r square by your radian is a 2 pi. Okay, so that will be 2 pi, and this will be 1 by 2 r square. So del A will be equals to your 1 by 2 r square del theta. Okay, so remember this thing, we will use it. Okay, so this is our very important equation, we will use it further. So moving forward, del A by del theta is equals to 1 by 2 r square, multiplying theta there and multiplying mass of a planet, numerator and denominator, we will have del A is equals to 1 by 2 r square m by m into del theta. Now this is just an area. If you want to find area and velocity, you have to take the derivative with respect to time. So let's take that. Moving forward, you have del A by del t, which is equals to 1 by 2 r square m del theta by del t. Del theta by del t is nothing but our angular velocity omega. Substituting the value, mass will be multiplied numerator and denominator, 1 by 2 r square m omega by m, and this m omega r square, this is nothing but our angular momentum, which is having a axis perpendicular to the surface of our motion. Like if you are moving in this plane, xy plane, so consider this is a z plane, okay, like this, and this is your motion, and this will be the angular momentum Lz. Okay, so substituting the value, you will have Lz by 2m. So you have came up with dA by dt is equals to Lz by twice m. Now very important point comes up. If the mass of sun and earth is conserved, like you have an isolated system and there is no external torque is applying in your system, then this Lz angular momentum which is applying in the z direction will be constant. So this proves that the aerial velocity with respect to aerial velocity is constant. Okay, now coming to the first statement, like we have proved the aerial velocity, but how does this first statement is like proving himself? So joining a line joining any planet to the sun sweeps equal area in equal number of equal time. Okay, so when you say this area, this is very using very high. Okay, like you think like, so here what is the concept is like the time it is taking for planet to move from here to here in like summer, in winters you can say that, like it is away from sun, so the weather is cool. So the time, let's say this is 1 day, okay, but in summer it is in near to the sun, so that area will be large and it will move speedily to maintain the area 1 equals to area 2. Like the planet has to cover the same area, so that should be it should have to increase the speed of that planet, and then the area will be equal. Okay, so this was all about the second law of motion. Moving to the further, next we have third law. Third law says the square of the period of any planet about sun is proportional to the cube of its semi-major axis. So it is a very common and usual term, like t square is directly proportional to the r cube, and if we are considering here a very like a common scenario with a circular motion, and we are considering a centripetal force. So centripetal force is m, like mass of earth velocity square upon r is equals to gm, mass of sun, mass of earth by r square, where g is our gravitational constant. Okay, you should know the value of g, which is 6.67 into 10 raised to minus 11 SI units. Okay, moving further, the mass of earth will be cancelled and one r will be gone, and velocity's value will be v is equals to under root g mass of sun by r. Now here comes the twist. So velocity is independent of mass, you know that, and the formula for velocity is v is equals to s by t. So with it we can easily find out the period. Okay, so t will be s by v, and for a circular motion that we are taking here and accounting centripetal force, the s, the a, the what do we say, the surface will be twice by r. So the period that we are taking, this will be twice by r by v, and we have the value twice by r by under root g m by r. Now always remember in your life, like when you have any proportionality that you have to show, you cannot show it in a rational value, it should be an integer. So if I'll take it above that, it will be r raised to 1 by 2, and r that will be r raised to 3 by 2. So you cannot show that like t is directly to r raised to 3 by 2. No, this is not the correct way. So the correct way will be, you can square both the side and this will be the result, and of course t square is equals to a constant c, and this is r cube, and the c will be your g mass of sun, your c will be 4 pi square g mass of sun. So this is your constant, and you have proved this third law of Kepler planetary motion. So okay, these are the three laws. Let's do an example about it. Okay, so yeah, a satellite is launched tangentially from a height above the earth's surface, as is shown in the figure. Okay, so first you have to find the velocity so that it just touches the earth's surface. So what is happening, like you have a satellite, like this is earth, and this at this height you have a satellite. Okay, at this height h you have a satellite. So this is the scenario, this is earth and this is your satellite, mass m point this. Now what you have to find, you have to find that minimum velocity with which the earth is coming toward the satellite is coming towards earth and touching it, like it will follow of course an elliptical orbit. Okay, so some of the main points you should have to be remember here, and that will be the parameters of an ellipse. Okay, so this dimension, like this parameter will be twice of a. Okay, and as you see, this is the radius of earth. Okay, this is the radius of earth, this is 2r plus h. So just write it down, we will use it further. 2r plus h, that will equals to 2a. Okay, so yeah, we have to use here the total energy which is conserved in all over the motion, throughout the motion, which is E is equals to minus gm mass of sun, mass of earth by twice of a. Okay, which is equals to the total energy is equals to potential energy plus kinetic energy. Yeah, okay, putting the value of kinetic energy and potential energy, kinetic energy is minus gm mass of sun, mass of earth by r plus h. Now here comes the twist, like you have to put r plus h because the orbit in which satellite is revolving is r plus h. This was the orbit. Here's the condition that we applied, that it's coming to touch here, but the orbit is r plus h. Okay, so this will be the match, and plus half m v minimum, with which square into mass of earth, half mass of earth v minimum square. Okay, so cancelling common terms from here. Okay, mass of earth, and multiplying this to both the sides so that it will be cancelled. So v minimum square will be equals to 2 into, taking that potential energy term here, mass of sun upon r plus h minus 2 into g mass of sun upon 2r plus